Whenever you like, Slava.
Yes, we can start. You see, the first speaker today is Sergey Buterin, and the title of his talk is on damping a control system of arbitrary order with global after effect on a temporal tree. Please.
Thank you very much. And first of all, I want to express my gratitude to organizers for the of our online conference, for the possibility to make this talk, and also for the very good organization. This topic is quite new, as I can judge, and that's why maybe the slides little not so good organized, but because they appeared not as at once, so during the last year, but so the topic is on damping control system of arbitrary order with global effect on the temporal tree, and actually we speak about the so-called quantum graphs. I begin with some literature. So quantum graphs are usually understood as differential operators on metric graphs, and such operators has many applications, and I have given on this slide some literature, just randomly maybe. But titles can indicate various applications, and there are even more applications. So, but all applications are concentrated at the so-called spatial networks. So this means that the variable parameterizing the edges is identified with, is associated with space variable. And in this talk, we speak about the situation when this variable will be time. But first of all, I want to give some simple example. So there are many applications and many examples, and maybe one of the simplest and best examples is elastic string networks, because they in equilibrium state coincide with the graph structure. And just for the beginning, I want to give some simplest boundary value problem on a star-type graph, a Sturm-Liouville problem. So we have a graph, all edges parameterized with x, varying from 0 to 1. 1 always corresponds to the internal vertex. On each edge we have a Sturm-Liouville equation, and we also have the so-called matching conditions at this internal vertex, continuity conditions, and Kergov condition. and also boundary conditions. For example, Dirichlet conditions for something like this appears after separating variables. For example, when we study the elastic string network, and continuity conditions then mean that the strings are connected, and Kirchhoff's condition means a balance of tensions. And almost all studies concerning quantum graphs belong to purely differential operators, but in our goal was to I want to speak about this, how this idea appeared. So first of all, the goal was to define an operator with constant delay on a graph. Operators with delays and with deviating other equations with deviating argument actively studied from the beginning, maybe earlier, from Euler or even, but actively studied from the middle of the last century in connection with many various applications. And almost all papers devoted to various non-local operators on graphs belong to the so-called, I call it local and non-local case, when the equation on each edge can be solved independently on the equations on other edges. For example, in our Chinese colleagues in 2021 considered such local and non-local operator on a star graph. So it differs from the boundary value problem on the first slide only by appearance of this minus aj. And each such equation can be solved independently on each edge because this delay is its own on each edge. So it doesn't affect other edges. And then one can obtain fundamental system of solutions and obtain characteristic determinant and so on. Then one can study properties of eigenvalues and solve various problems. But in our case, we want to consider the so-called globally non-local cases. So I give first example. This globally non-local case appears even on an interval. For example, we have a boundary value problem 8 with Dirichlet boundary conditions on the interval 0, 2, and with delay A. Delay is from the same interval. Then we also have that Q equals 0 almost everywhere on this interval. It's actually the so-called zero, the case of the so-called zero initial function. So it's quite natural to consider such situation when Q is 0. Then we can define new functions y1 and y2 in this way, and q1 and q2, and obtain two equations. But each new equation is defined on the interval 0, 1. Then we automatically have continuity condition for this function and for these functions and for their derivatives. And also we have a boundary condition. We'll take this for 12. And then we additionally should define the function y2 in the second equation. And we define this by this relation for example, if A is less than 1, then this equality will hold on 0A. And we put Q1 equals 0 on the corresponding interval 0A, if A less than 1. And another situation when A is greater than 1, then we define a little differently. And so this relation 13 means that the delay propagates through the point V1. So we have boundary value problem on a simplest graph consisting of two edges with one star graph with one internal vertex, and the delay propagates through this internal vertex. So this situation actually natural even for an interval. And this situation can be automatically generalized for an arbitrary star graph. For example, we can consider star graph, and parameterization of the edges will be in this way. So the first edge is from 0 to 1, and other rest edges from 0 to 1, 2, but only first 1 corresponds to the internal vertex only on the first edge. And this situation was considered in this paper, where some also inverse spectral problems were considered and studied for such global and non-local operators with delay. And also a definition was given for such an operator on an arbitrary tree. Then here we have boundary value problem for a star graph. So let us see. We have a delay from 0 to 1 to 2. The corresponding boundary value problem will consist of m equations. Each equation has the same delay parameter. Then we have condition 16. Condition 16, that means the propagation of the delay through the internal vertex. And also we have also continuity conditions and the Kirchhoff condition. And for example, again, Dirichlet conditions, it is boundary vertices. And some condition on the function, on the potentials. For example, again, if A less or equal 0, then we just have that the function Q1 equals 0 on the corresponding interval, OA. And the rest functions Qj are arbitrary. And the initial function, all equations in 15 for j greater than 1. So all equations except the first one. We have one and the same initial function determined by y1. So this on this picture we can point out here we have y1, and this serves as an initial function for yj on the rest edges. So it's also quite natural situation. If m equals 1, this star graph with two edges, and this coincides with the case of the interval. And so my plan was consider some other problem for such under such settings, and I considered the problem that was so the problem of damping a control system with delay. And this problem was, so this, I have made some talk on some conference, and Professor Skubachevsky advised me to look at this problem, and it was 1 year ago, and I extended this problem first on star type graph, and then to arbitrary tree, and then to arbitrary order system. First, this problem was posed and studied by Krasovsky, and let me formulate. So, and then Skubachevsky considered this generalization of this problem to the equation of neutral type. So Krasovsky studied the case of retarded type when A equals 0, also with constant coefficients. And Skubachevsky considered the case when of neutral type, and A is so non-zero, all coefficients first were constant and real valued. And so the problem is as follows. So we have some equation, 20, and we have a prehistory. So this actually it's control system. So the function u is control. We have prehistory of this system is determined by the condition 21 with some w21 function phi. And then the problem is to bring the system into the state, actually it's equilibrium state. So when y equals 0 starting from some t. No, for definiteness t is greater than 2 tau. Tau is delay. And it's sufficient to find, for this purpose, it's sufficient to find a control function such that y becomes 0 on this segment, or interval, doesn't matter. And obviously, this function is not unique. And that's why there arises the variational problem for such energy functional. So the problem is to minimize this functional under the conditions 21 and 22. And in the work of Skubachevsky, there are, in particular, there are two theorems. The first theorem is that the function y from this class is a solution of the variational problem if and only if this function is a solution of the boundary value problem for such an equation 24, under the same standing conditions 21 and 22. Well, equation is quite big, quite maybe, but it's that doesn't matter. The main maybe thing here is that the solution is understood in the generalized sense. This means that this combination should be absolutely continuous. No, actually, it's absolutely continuous, and automatically this will be from this class because there may be no usual solution, even if the function phi is very smooth, maybe infinitely differentiable. Because of the matching condition. And Skubachevsky, and this problem appears only for A, it's obviously, appears only for the neutral type when A equals 0, when A is not 0. Otherwise, the first derivative, the first derivative will be from this class and it will be usual solution. And this boundary value problem has a unique solution, as well as the variational problem has a unique solution, and there is also such an estimate for the solution. And let us now consider the case. So let us first consider the case that I studied, the case of the star type graph. So this so we will consider this graph. In this preprint, result theorem 1 and theorem 2 were extended to, in the case of retarded type equations, so simple case, when simple because there is no general solution, was extended to an arbitrary tree. And let us illustrate the results first for the star type graph. In up to time t, so let up to t equals t1, up to this moment of time, our control system is described by this equation of the retarded type, for simplicity and first, and then y1 is defined on the first edge here. And we have also the prehistory of the system. But at the internal vertex, V1, the system splits into m-1 independent processes described by the analogous equations, but with different, maybe Bj and Cj, with different coefficients. No, here we also assume that coefficients are real valued and constant. So this equation, these processes are independent, but they have a common history determined by the equation on the first edge and this condition. So for example, condition 29. And here we have also condition 29. This conditions, they mean that the delay propagates through the internal vertex. So this came from the previous part of the talk. And besides 29, we impose also the continuity conditions. And these continuity conditions, they are agreed with, how to say, they are coincide with these conditions if we allow t to equal 0. But it's natural to divide these two types of conditions. And then we fix on each edge, outgoing edge, we fix Tj for definiteness again, Tj greater than tau, and then dampen this control system on the graph would mean that Yj becomes 0 for such t. And for this purpose, it's sufficient to find such controls that bring the system into this equilibrium state. So there can be some interpretations of this statement of the problem. So, for example, it can be interpreted that one interpretation is not all reason, so to say, processes that appear arise at the internal vertex. So they are all not all really exist, but they are just possible scenarios of one and the same process after this point. In other words, so there appear m-1 different scenarios at this point for the further process flow, and they are differ in the coefficients. So each scenario has its own coefficients here. But before this time point, there is no information about which scenario will be really fulfilled. And that's for this reason, the controls should be chosen in such a way that the system will be damped surely at each possible outcome. That is on all edges, on all outgoing edges. And in this connection, so no, it's of course, since such controls are also not unique, far not unique, so it's natural to reduce the corresponding efforts. But when we construct the corresponding energy functional, we can use some positive weights. For example, in accordance to probability of each outcome, or maybe from some other reason. Just we fix some A alpha J and consider this energy functional. So we arrive at the variational problem for minimization of this functional under all standing conditions. And this theorem 3 says that solution functions yj form its solution of this variational problem if and only if they possess additional smoothness, and they are solutions of the boundary value problem B. And this boundary value problem B is on the next slide. It consists of m equations. So this equation on the first edge, and this equation on the other edges, also along with all standing conditions. And there appears also Kirchhoff condition 33 with such coefficients. So this boundary value problem has a unique solution, and the variational problem also has a unique solution. And this solution can be estimated by formula 35. So this a priori estimate holds. And in 22, this theorem 3 and 4 were generalized to a control system of arbitrary, even arbitrary order, and Noethel type, and even with non-smooth complex coefficients. But first of all, I want to give some examples, maybe to better illustrate this problem. So example 1. This example means I told before that there are several possible scenarios, but consider the situation where all scenarios are equal. So this means that B, J, Cj, and Cj don't depend on J. So we have on all outgoing edges, we have one and the same equation, actually. So we have m-1 copies of one and the same scenario, starting from the point T1. So we artificially reproduced copies of one and the same scenario. And then for constructing the energy functional, we use this such weights. No, these weights can be interpreted as probability. So the probability of the first edge equals 1, and the probability, the sum of the other probabilities equals also 1. And for example, each scenario, each copy has one and the same probability. So 1 over m minus 1. And by the symmetry, the solution of the corresponding boundary value problem contains m minus 1 equal components by symmetry. Otherwise, if these components were not equal, then the solution wouldn't be unique. I wrote here. Otherwise, yes. So they have equal components. And for this reason, one can reduce the number of equations in this boundary value problem can be reduced just to two equations. The equation on the first, the equation corresponding to the first edge, and and one equation is corresponding to other edges, but we can sum up all these equations because they have one and the same solution. And it's one of the same equation. So multiply with m minus 1. And then we all other conditions will take the form 39. All conditions except Kirchhoff condition. And Kirchhoff condition has the form 40. So actually, this problem, in particular, if B1 equals B2 and C1 equals C2, this problem, these two equations and all the conditions, this problem takes the form, this form, now let me show 21, 21, 22. So the corresponding boundary value problem on an interval, 21, 22, and 24. When A equals 0, so retarded type. And the function y will be constructed from y1 and y2 in the natural way, this way. So the conclusion is that artificial reproducing copies of one and the same scenario, starting from a certain point of so we can consider originally we can consider the situation of an interval, and in some point of this interval we artificially reproduce copies of the first scenario, and this situation would lead to the same optimal control as in the original interval case. No, it's natural. And another example, also here we have simple example when scenarios are really different. So first we consider the simple control system 42 without any delay and so on. And so one should find such U that the solution would satisfy these two boundary conditions. And the optimal control is a solution, is a unique solution of this boundary value problem. And here we need to find such optimal control, but we don't know what T is. T may be either 2 or 4. And the precise information about this T will be available only at T equals 1. And the main question here is which control should be chosen before this time point. So if we know for sure that T, for example, equals 2, then we just solve this problem And or alternatively, if we know that t is 4, we can solve this problem and obtain the optimal trajectory. Then we put this, substitute this optimal trajectory in this equation and obtain the corresponding control. But we don't know what t equals to. And an answer comes when we extend this problem to a 3-star graph that takes into account both possibilities. Here we have picture. So the time point 1, when t at which the value of t becomes certain. And then we have two edges. One edge corresponds to the case t equals 2, and the third edge, corresponds to the case of t equals 4. And then we denote y1 trajectory, a common trajectory. This trajectory should be common on the first edge, and two possible trajectories on the other edges we denote by y2 tilde and y3 tilde respectively. And then we arrive at the control problem on this graph. This control problem. So we have corresponding equations on each edge, and then boundary conditions, so initial condition and target conditions. And also we have continuity conditions, because the process is continuous. Continuity conditions. No, here we denoted just to use the parameterization of this graph, we make this designation. Then we assume that probability of t equals 2 is p and 1 minus p is the probability of t equals 4. And then the corresponding energy functional for this is alpha 1 equals 1, alpha 2 equals p, and alpha 3 equals 1 minus p. So then we have the corresponding boundary value problem for this for the optimal trajectory. This boundary value problem consists of homogeneous equations, but equations of the second order, and also Kirchhoff type condition. Here we have, it's easy to find optimal trajectory, and here we can so y1, y2, and y3. And here we show these trajectories. So this line, the lower line, is this line y1, 2, corresponds to the case when t equals 2, definitely 2 from the very beginning. And here 1, 3 t corresponds equals to 4 from it's definitely from the very beginning. And here we have the trajectory in presence of the uncertainty on the optimal trajectory on the graph y1, y2, and y3. No, it can be seen that each trajectory 1, 2 is shorter than the corresponding composite trajectory, and the same applies also to the other situation. But the composite trajectories allow one to take more advantageous position, so in presence of uncertainty. So when we don't know which outcome will appear, then we achieve this medium point, and then we already, when we know which t really is, then we can turn to this to this possibility or to this possibility. And if and this point, by the way, this point y1 in edge 1 sweeps over this entire interval as soon as p probability ranges over 1 to over the interval 0, 1. So for example, the less p is, the closer this composite trajectory will be to the trajectory y1, 2, and conversely, the composite trajectory y1, y3 tends to this trajectory when p increases. Tends to zero, conversely. So let us now consider the general case. So the case that was studied in this paper, and unlike the usual results in this direction, usually only equations of the first order were studied, but here I considered equations of nth order and with variable coefficients and even non-smooth coefficients. So all coefficients from L2 and the senior coefficients and from L infinity. And then this is because such results are new even for an interval. Let me first show them on the interval. So we have prehistory of the system. We have the entire function, initial function, 50, and then we have initial conditions. So this example, this shows that initial conditions are various different type of conditions, and they cannot be in general. It's not natural to combine them. So this condition this is a functional differential equation. So the first condition determines initialize this functional part, and these are initial conditions for the differential part. And then we fix some t for definiteness greater than 2 tau, and want to find control that brings the system into the equilibrium state 52. The corresponding energy functional, because this all functions involved are already complex valued, then we have such modulus under the integral. But here we should. So this case is more general, even the neutral type. This equation of the neutral type, and here there should appear generalized solution, and for this reason we introduce the quasi-derivatives 54, such quasi-derivatives, in sense of which we will understand our generalized solution. And then the results for this situation, the results are contained in theorems 5 and 6. Theorem 5 says that y is a solution of the variational problem if and only if it obeys the conditions of the absolute continuity of the corresponding quasi-derivatives, and is a solution of the self-adjoint. This problem will be self-adjoint as in the previous cases. The self-adjoint boundary value problem B for this equation. So the last quasi-derivative equals 0. So using quasi-derivatives also useful because convenient because this usage allows one to represent the equation in very concise form. So this equation under all the standing conditions. And the second theorem, the boundary value problem, has a unique solution, satisfying this estimate. No, satisfying this estimate is actually the second assertion. And here I have some slides about comparison of the introduced quasi-derivatives with classical quasi-derivatives for ordinary differential operators. Here I put some references. No, for example, in the book of Nymark, maybe everyone who used this book have noticed that in the second part, quasi-derivatives were used for some spectral problem, for the problem of studying symmetric operators. So it's quite a natural situation, even that quasi-derivatives are used in connection with spectral problems. And let us try to compare this introduced quasi-derivatives. So if we the problem of the purpose of using quasi-derivatives is to regularize singular ordinary differential equation with singular coefficients. So, for example, these coefficients can be even in negative Sobolev spaces, so understood as distributions. And this topic is quite actively studied during the last quarter century after the works by Shkalikov with his students. And in this connection, all quasi-derivatives, for example, for even order ordinary differential expressions can be arranged in accordance with their strengths. So the more strong singularity they can overcome, so they can regularize, the more strong quasi-derivatives. So quasi-derivatives one can introduce in different ways. And for example, the most strong quasi-derivatives for differential operators of the second order, of the even order, were introduced in this work by Mirzoev and Shkalikov, and they can they can regularize this expression for such coefficients. So here we have that coefficients from negative Sobolev spaces. Now, in particular, for the Sturm-Liouville operator, this situation corresponds to the case when Q is from W2 minus 1. So this means that Q is the derivative of some sigma, and sigma from L2. And the quasi-derivative is determined in this way, and the corresponding quasi-differential equation has the form 63. And actually this coincides with the expression 60. But expression 60 can be considered without using quasi-derivatives, but quasi-derivatives are needed only for solving this equation, because in order to reduce this equation to integral equation, for this purpose we should have integrable coefficients. And here we have integrable coefficients. Here actually we have a system with integrable coefficients. And they introduced here in this talk quasi-derivatives have actually the same strength than that quasi-derivatives used by Mirzaev and Shkalnikov for even order operators. And for the second order, this quasi-derivative so that I introduced, actually this quasi-derivative has very similar form, but the corresponding potential in the Sturm-Liouville equation would have such form. So all this means that all potentials for which it can be used are such functions for which this Riccati equation has a solution. Now, if Q is a real valued function, that's precisely Miller potential. Otherwise, if Q is complex function, that this equation can be made solvable in any case if we add some sufficiently large constant to this potential. So if we replace Q with Q plus C, where C is sufficiently large positive constant, then this equation will have solution from L2 in any case. So this gives, in some sense, alternate this new quasi-derivatives. The main difference of the introduced quasi-derivatives is that they are non-local, but in particular they can be made local, and then they give some alternative regularization. For example, in this case, for higher order, it's somewhat an open question if each situation can be reduced to the case when one can introduce quasi-derivatives. No, here we have also other examples. For example, that introduced quasi-derivatives in the particular case when n equals 1. So when we have such expression. So the case when was considered in this paper by Skubachevsky, then this introduced quasi-derivatives has this form. And it can be seen that the concept of generalized solution in this paper coincides with the generalized solution in sense of the introduced quasi-derivatives. And the example 3 shows that for n greater than 1, there can appear generalized solutions even for retarded type equations, not only for neutral type, as for n equals 1. For retarded type equations, even in this situation, there can appear generalized solution. So the solution whose derivative from second, in this case, in second or third derivative can lose smoothness. Here, the third derivative can lose smoothness. But the corresponding boundary value problem is of order 4. And finally, I want to briefly show the results for arbitrary tree. So we have some tree, some set of vertices and edges. We have boundary vertices and internal vertices. We introduce some numeration. For example, each numeration of this edge is as here. The last point of the edge has the same index, and the first point has index kj, and kj is it's some mapping. It's mapping of the first of the set of the first m natural numbers to this set. This mapping uniquely determines the structure of the tree. For this picture, we have concrete values of this kg. And then we, as usual, by a function on T, mean some tuple. Each component yj defined on the corresponding edge ej. Tj is the length of this edge. And then we also consider the so-called extended tree. Extended tree is nothing else than as that the first edge is supplemented by this interval, just to specify the initial function for the entire tree. And then we have control problem on the, actually it's Cauchy problem. We have the corresponding control problem on the entire tree. We have equations on each edge. We have the conditions of propagating the delay, propagations of the delay through the internal vertices. We have many continuity conditions at the internal vertices, prehistory of the process on the entire tree. And we have initial conditions for the entire tree. The coefficients also from the same class as in the previous example. So from L2 and the senior coefficients from L infinity, 1 over b, and b also is L infinity. This Cauchy problem has a unique solution. One needs to find the control. For simplicity, we have alpha j equals 1, but one can also consider alpha j here, some various positive numbers. And the variational problem is to minimize this functional under all standing conditions. All these conditions. We introduce also quasi-derivatives. So this will be globally non-local quasi-derivatives because they actually have both variable delay and variable advance. And then we arrive at the corresponding boundary value problem, which is defined on all functions on the tree that obey the absolute continuity condition for the corresponding quasi-derivatives. So we have equations of order 2n, all standing conditions, and also Kirchhoff type conditions. So in each internal vertex, we have additionally n Kirchhoff conditions. And then we have, finally, we have again two theorems. One theorem is that this variational problem is equivalent to boundary value problem. So, strictly speaking, solution y is the solution of the variational problem if and only if it obeys the conditions, so absolute conditions of the absolute continuity of all quasi-derivatives, no, except only the last one, and solve the because the last one is 0, and solve the boundary value problem B. And theorem 8, that the problem B has a unique solution. Actually, this theorem can be, maybe it would be more natural to formulate as that the variational problem has a unique solution. It's equivalent. Has a unique solution, and this solution satisfies this a priori estimate. So, no, and I think that's all.
Thank you very much.
Very much.
Please, any questions?
Hello. Hello here. I'm Abdon. I would like to a couple of questions. That's possible?
Yes, of course.
Yes, about the damping system. Damping means some constants you showed at the start in some slide are not zero, right? So
could you please
damping? You call about damping. It means that in the system Sergey considered is some constants in the system are non-zero, right? This is the meaning.
No, damping means that the system becomes is brought into the equilibrium. So this means that the function y is equals 0.
But after some time, because
But
you see
from certain time, one should choose time t, and then one should damp the system after this time.
Yes, but you have a differential equation with control, and then this differential equation you have with constants. This constant should be in such a way that this stability exists. So, right?
Stability. But the question of stability, no, I don't consider. You mean Lyapunov stability?
Yes, but you assume that the stability there is, right? This is the question. So,
I don't consider this question. Actually, we have of course, maybe it's question important, but usually in this problem, this question is not considered because t is fixed.
But how can you assure that at this t you will be able to arrive to certain state? So my second question is about the controllability. So how can you assure how you assure that you have controllability of the system? Controllability means that you can start in some state and finish in other state, and you will always have a control. So this is controllability. So and you are looking for control systems. Then the natural question is, do you have a controllability? So the criteria of controllability.
So
criteria.
Yes, as I understand, the controllability means that such control exists.
But for this time and for every state.
Yes.
Yes.
Because it's for this problem control. This is a trivial question because no, for example, let us see the problem 20, 21, and 22. And then we want to find such u that this system has a solution. So otherwise, from the other hand, we can take any y that satisfies 21 and 22, and then substitute this y into the equation, and then we obtain the control.
Yeah, but it's just that you have you should have some condition in ABC. So
ABC it's coefficients.
Yeah, but okay. So yeah, okay. And just one other questions about the simplest equation you showed. So y dot equal to u.
This.
Yes, this is interesting. So, but here is no, so then here is no damping, right? So nothing. So you have just simplest 42 system, and then when you speak about optimal control, you speak in the sense of the energy, right?
Yes. No, so the norm of this U should be minimal.
Yes, but
and then we have
yeah. Okay, yeah, yes, that's fine. So okay, yeah, and but you use here some to prove that you use some so by hand, or how you prove that, so that this control is this optimal control is such a way so this control is satisfied for 43.
Actually, this is very particular case of the theorem of theorem 2 of this theorem of theorem 1.
Okay.
So you see, if we have A equals 0, B equals 0, then we have the second derivative equals 0.
Okay.
So, and the proof is, so it's just a consequence, just a corollary from the theorem. But the proof is actually is that no, one should consider bilinear form.
Okay.
And as I know, it's just standard way.
No, well, yes, you could also apply Pantriagin's principle there. So in case, yeah, okay, yeah, but your control is not bounded, right? So you're nothing. So you have, yes, you have boundaries. Actually, you have boundaries because you have the energy is bounded, right? So it should be because it's L2, and you have a bounded control actually. And then it's better to use actually it could be you could use also the Pantriagin principle to prove that equation for the not with probably it's also done with delay or neutral things, I think. Okay, that's it. Thank you.
Thank you.
More questions? If there is no question, we have to thank the speaker for the nice talk. Thank you very much.
Thank you.
So, and we have 10 minutes break.